He leads off. Doing pretty helpful ago. Yeah, so I think that one happened. So
More visible, right there. To rotate a little bit. Scroll.
redoing.
Yeah.
Like happens.
All right, welcome back, everybody. So we switch gears now, and Kontu from BNL is going to speak about physics of the electron-ion collider from the experimental point of view.
Okay, thank you. Thank you, Alexei, organizer. So it's very my pleasure to be here. My office is across the hall. So if you have questions, come to me. So this is the title. I want to explain a little bit what I wanted to talk about today. Okay, so we are at the era of that AI is going to take over. Okay, believe it or not, like it or not, they're going to take it over. So if you look at a specific problem, you type it in, what is the electron-ion collider, how to do structural function, how to do imaging, they will provide an answer better than any of us can provide. But one thing that AI hasn't catch up yet is that I call it the physics intuition. It's like human beings, the brain, the way that they're wired is still more advanced to some degree, that you look at some problem, you can connect from different fields, you can connect from many different things, and you kind of have an intuition, although you don't know exactly what the answer is. Okay, and that is a unique capability of what we have. And I think for the next generation, like all of you guys, this might be the determining effect or the factor to make you a successful physicist or successful anything. Okay, so I will try to do very slowly, trying to build a physics intuition about the electron-ion collider physics. How do we go from what we don't know, and you think about these questions, and step by step towards what we have known now. So I call it, this is the with a dummy, okay? So it's really like trying to take it slow. And I quoted Stephen Hawking, remember to look up at the sky, the stars, and not down at your feet. So the modern version is not look down at your phone and trying to ask this question, right? This as a human beings, the inner question, what does the universe look like? So about myself, I just give you a page. You can check it out later. I'm not as famous as other lecturers. So just trying to tell you, I'm an experimentalist. I do QCD. I'm at Brookhaven and also at Stony Brook. I do many experiments. I probably do more experiments than any of you in different area and different type. So this is the physics intuitions I wanted to build as an EIC person. Okay, there will be 3 lectures. So it's a step by step. So the first one is about the intuition, how to study matter, right? We're trying to study the visible matter at a very small scale. And the second one is that for the EIC physics specifically, what are the big questions? What are we asking? How are we going to do it? And then why are we doing this the way that we're doing it? And the third one will be a little bit more, reality check. What are you dealing with in the machines? What are capabilities? Okay. So I think 90% of my time, so this is not evenly distributed. 90% of the time will be on number 1 and number 2. And then number 3, I will flash through because it's kind of boring, $3 billion here, a couple hundred millions. You can look it up. Use your AI. Okay. So a few tips. I wanted to, at least for these lectures, forget about who you are. Okay. Take off your hat about you being a theorist or experimentalist. You're just a theorist. You're just a physicist. Okay. Just trying to be a physicist and try to build a picture. Okay. Sometimes you really have to explain it. You have to build a picture in your mind to try to understand something. Equation is very, very powerful. As a lot of, you eventually have to be relying on it. But having a picture is so unique and so useful. And finally, give it a guess to things that you don't know. Try not to just look it up instantly. Trying to take a guess. There are 3 advantages I'll call it for taking a guess from your physics intuition. Because first one, if your physics intuition is correct, you feel really good about it, right? I'm the king, I'm the best, I can guess, fundamental physics. The second one is your intuition is wrong. And then you really learn why you guess it wrong, right? I mean, it makes you remember. And the third one is that if you are not sure, that's exactly a new idea in research. You're trying to find out, right, about physics intuition. So it has all the benefits. Okay, so let's start. So what we talk about, this is a video made by CERN. Many of you probably have watched this before. And they're trying to tell us how do we understand the visible matter. So then you're going from, a macroscopic scale, going down to the human hair and going down to different, structures. And then eventually, as a high energy physicist, we are zooming in to the smallest scale. You cannot go even smaller. So we sometimes very proud because we study the smallest thing in the universe. And then when you're going down to atoms and you have nucleus, and eventually to the hadronic or hadrons, the protons. So one thing that at CERN, as you can see, a very important ingredient was not put into this video, right? So I want you to have that question in the mind. What is the very important part is not in this video? So the things that what we do for EIC is that I call it the seeing is believing. It's the so-called power of imaging. So this is the very natural way to study something, right? You wanted to take a look of what you're studying from the largest scale, from the black hole. I mean, black hole by definition is that the light cannot escape, right? But still, you wanted to have a way to reconstruct what the black hole looks like. How cool is that? And you go down to all of this from medical physics, from biology, from everything. You're trying to take a picture. If you're, having something in your body, you go scan it. You immediately know there's a problem. So this imaging is a fundamental technique in research. So what we are doing is going from the largest scale to the smallest scale. And I think is one of the most convincing scientific methods of study. So I think Fred already talked about this briefly. So one thing that for high energy physics, the starting point is the Rutherford scattering, right? Everybody heard about Rutherford scattering? So today I'm going to do a little bit different. Is that the Rutherford scattering is about almost more than 100 years ago, right? The idea is that when you don't know what's inside, you're trying to hit something with it, right? You're trying to shoot some particles and you're trying to study the behavior. And we all know the answer, right? Who doesn't know the answer? Everybody knows the answer because the Rutherford scattering is that you have alpha particles and then you're trying to hit it with this gold foil. And then at the very beginning, you think, okay, if this is uniformly distributed, you will have some expectation, you have scattering. But then eventually the result is that most of the particles go right through, right? They just go right through. It's like there's an empty space. There's a few events with this large scattering angle. Remember, everybody taking this class? Okay. So now let's do an exercise. I wanted to try something with the Rutherford scattering. And then you wanted to build this intuition that the geometry, the scattering problem, is fundamental for EIC from the very beginning, 110 years ago, right? So in this very early 1900s. So now you know the answer. You have alpha particles, and you're trying to shoot it with some foil. And we know that you have a point charge, right? It's a nucleus, and then everything else is almost empty space. So if you're hitting right at the center, what's your intuition? You'll backscatter because you have a very strong, you have initial momentum. But then if your alpha particle coming from somewhere on the side, very large distance, you're not going to have any scattering, right? You're going right through. So based on this very simple picture, then you can say to write down this has some dependence on this. We call it the impact parameter, B, okay? Impact parameter. It's basically the distance that you're going through with this nucleus. So now you can guess, okay, what will be the dependence on this impact parameter? And then if you're doing here, you would do a large scattering angle. But if you're going here, it will be a very small scattering angle, right? Very qualitative. You don't even need to know any about like QCD or any high energy physics, just simple geometry arguments. So then you say, okay, theta which is this scattering angle, is related to 1 over b, right? Because the closer you get, the larger the angle they scatter, the further away you get, the smaller the angle, okay? So now pure geometry comes in, the scattering problem. Now you're looking at, imagine that you are the alpha particle. You're trying to hit somebody, right? You have a two-dimensional space, right? You have this area, and then the probability is basically in high energy physics called cross-section. So forget about the term cross-section, just probability hitting this guy, okay? So now we say the probability, even 2,000 years ago, in the Asian in the Chinese culture, they said, I don't know how to do it with the calculated area of a circle, but I know how to do it with the square. So the way that they did it is that they put all the sand, go to the beach and put the sand on a piece of, plywood. They don't have plywood at the point, but some board. So they weighted how much the sand weighed, and then they cut it with the circle, and then they put the same sand, keeping relatively thin, and they can get the ratio between the square and the circle, and then they get the area of the circle, right? So now it's exactly the same, right? You're trying to shoot some particles, trying to get what's the probability of hitting the target. So now your A, which your area is like this, pi r square, right? So now your r is basically the distance, it's the radius. So now if you want to do first year calculus, you can say, okay, so what about this this thing, right? Right? So this will be the area, the probability, and then basically the probability of hitting something will be related to the geometry. Okay? So now you plug it in. Now you try to plug in. So you can say dB d theta. So eventually is that here is basically b 1 over theta. So you have a 1 over theta dB. You have another the idea is that after you plug it in, this simple number, it becomes 1 over theta to the third. Simple geometry. Okay? So now, after you have this scattering angle theta, but it's only one dimension, you have actually, we call it the high energy scattering, you have this solid angle. So remember from your geometry or calculus class, from angle to a solid angle, what was the relation? So basically, the solid angle is this, I think, with the sine theta, right? D theta. So when theta is small, it's basically a theta. So eventually, if you plug all this in, the Rutherford scattering becomes dP. I wanted to keep it as simple as possible. Okay? 1 over theta to the 4th. You don't have to know any about high energy physics, just geometry. You hit something, 1 over to the theta to the 4th. So that means when you do this scattering problem, the cross-section drops a lot, right, with the theta. And that is a physics picture I want you to remember. This is very important. Where's my clicker, actually? Where's my clicker? Oh, here. Sorry. Okay, so this is the Rutherford scattering. Okay, let's just look at a history. So basically, you have an alpha source, you have this scattering, and you want to have some screen, right? So this friend actually talked about it. So the original model is called this Thomson plum pudding, right? So basically, it's a uniform distribution. I already talked about it. But eventually, what actually observed is that you actually have mostly going through, but you have this backscatter. And this is exactly what happens, 1 over theta to the 4. So now you look at this. Of course, the form is not exact, but sine theta to the 4th and theta to the 4th, very similar if you plot them, unless you go into very large angle. And then this is something that I use exactly this to write a Python script. to visualize what this scattering looks like. So this scattering is purely by geometry that you have this 1 over theta to the 4th scattering. Okay, so this picture is very important, and the geometry actually dominates in this scattering process. So now moving on, the next thing that people would try is that now I have alpha particle, I have a, I know there's a nucleus in the atom. So they start the technology involves. Now you can actually accelerate electron, okay, the electron. So now I wanted to ask you, what happened when you use an electron with a nucleus or proton? What happened? What would be the scattering looks like? Oh, not that, but what would be the scattering looks like? Anybody wants to take a guess? While I'm going through my notes. There are two things that are going to change, right? First one, the electron is very light. So you're going to have the electron accelerate almost at the speed of light. So the relativity effect should come in. And then also the electron,
Do we need to worry about like the radiation from an accelerating charge?
Yeah, but later. Let's think about there's no radiation. I mean, we're going, if you're bending, of course, we have a lot of radiation. But right now, don't think about radiation, just the electron, okay? Pure thought experiment. Okay, yeah.
Slight magnetic moment correction.
Uh-huh.
That's where the electron, you'd need that. And you were saying the relativistic correction.
Yeah. Okay, that's good. It's good. So what will be the consequence of it? What will be, my question is, Rutherford scattering is 1 over sine theta to the 4th, right? What will be with replacing with this electron?
Can you repeat the question again?
So now I replace alpha particle in Rutherford scattering with the electron. They're going very, very fast. What will be the scattering angle relation? What's your guess? Okay. Unfortunately, I only have 15 minutes, so I have to move on. So the idea is the following. So now I can erase this. So electron, as we know, has spin. So electron has spin. So one thing the electron doesn't like, so you have a target, it goes this way. If it goes 180-degree backscattering, let's say it's not the case, but let's for a second assume that the electron spin is also going to the same direction as the momentum, right? Helicity plus. Remember this term? Spin and momentum are the same. So then if this is in the speed of light, you're going to a backscatter. The electron hates it. Why? Anybody guess why? Electron hates the backscatter? This is easy. You guys have learned this before. Okay, let me remind you. At the speed of light, mass has to be 0, correct? We have a term called chirality. Is your, chirality and helicity becomes the same thing. And helicity is momentum dotted with your spin. So at the speed of light, chirality is strictly conserved. You cannot flip your chirality randomly. So imagine you have an electron hitting a wall and going back. And physics, just so strange, will not allow it because when the momentum flips 180 degrees, your spin, nothing is changing the spin. So helicity becomes from plus to minus. And that is not allowed. So in this scattering problem, you can do a lot of angle, but this backscatter, this electron scattering hates it. So it's not allowed. So when it's not allowed, because of this helicity argument, so the Rutherford scattering, right? The Rutherford scattering, so now I use sigma, which is probability, right? This scattering was some factor, you see that, which is not so important. You have sine to the 4th, theta over 2. And you just have to have a term to describe the behavior that electron hates to be backscattered. So actually, if you do cosine, and that will do the job because when, theta, is at, 90 degrees with cosine, it's basically 0. So the whole term will drop to 0 for 180 degrees backscatter. Okay, that's the idea. This is called the Mott scatter. Okay, so from Rutherford scattering to Mott scattering, you only add the spin and the relativity into it. And all of a sudden, the behavior changed a little bit, but significantly, because the electron doesn't want it to go to backscatter. Okay. So now, after this backscatter, in the 50s, Hofstadter is a famous physicist, had the Nobel Prize for it, is that after Rutherford scattering, the Mott scattering, he had an expectation. He built an experiment trying to find out what the proton looks like, right? We're slowly getting into what the proton looks like. And the expectation is that if the proton is a hard sphere, no inner structure, that will be exactly like the Mott scatter. You have an electron, you're hitting the hard sphere, you should not be backscattered, but the scattering distribution or the cross section should be something like cosine square over sine to the fourth. It actually looks very similar to this, but it actually drops very fast, and then at the 80 degrees, 180 degrees, that it actually quickly drops to zero. So that is so-called the Mott curve. And then they basically do some renormalization, and that is expectation. So now the Hofstadter actually make the experiment and look at where the data is. Okay. So why is the data so much more suppressed as a function of angle? It's not like a Mott scattering. Now, question to you, why is that?
Point-like particle.
What?
Like,
No, point-like particle is like the Mott curve.
yeah, so it's more suppressed because it's an extension, like in real life.
Okay. Why? Why is the suppressed not over or something else? Why does it behave the way it is? The structure inside. Okay. But why there's a structure inside, it goes down? It goes more suppressed.
Getting in the way,
Sorry?
because it's getting in the way.
In a way. And then how? Why is it suppressed? This is fundamental to EIC, okay? We're doing this every day. We're hitting something. We wanted to see if it breaks up or not. So now I give you an example. This is the data, right? This is the data. It's like this picture. You kind of have a balloon. If you hit it really hard, it's gonna break. So the cross section actually disappear. You're not gonna measure it. So in the Mott scattering, you hit something and you expect to have a scattering angle. You still get the stuff that you're hitting with. But if you hit it so hard, it's not fundamental particle. It's gonna break. It's like this balloon. You're gonna poke it very, very carefully. So when you go into large angle, okay, in the elastic scattering, that means the angle is large. You're hitting with more energy. The scattering angle and the energy are not independent. These are one variable. The angle and the energies are related. So the harder you hit, easier it will break. So when you go into a larger angle, meaning you're hitting with large energy, the things almost disappear, right? If they look at this scale, 10 to the minus 33, this is very, very unlikely to happen. So that means you cannot hit it very hard. You have to tickle it. Otherwise, this thing's going to break. This is such a clever experiment to say, because the proton, the target you're hitting, actually has some stuff in it and is not indestructible. It has structure, and because of you have structure, it can be broken down. Okay, so this is the famous Hofstadter experiment. You can read the original paper. It's quite long, but the idea is the following, right? So this is the experiment. So the experiment winning him a Nobel Prize is that the proton has a finite size. You cannot probe it as hard as you want, because if you want it to be elastic, stay intact, it has to be some, very suppressed relation relative to Mott. We all know the answer. Quarks made up proton. Proton has quarks, right? It has inner structure. But at the time when they did this experiment, they still don't know what's inside. They only know that this is an extended object, like you said, and you can break it up. So finally, Hofstadter actually introduced the idea form factor. Okay. As a non-English native speaker, I have no idea what it means when I learn it. Form factor. So anybody give me an answer. What is a form factor? The idea is the following, right? So you can think about this question. So now I have the Rutherford scattering, okay? And then we have the Moss scattering because I use electron. Now the cross section actually doesn't look like this. It's even more suppressed. I need another function to be less than 1. So this thing is called form factor, right? So it's basically Rutherford plus spin and then form factor. So anybody, what's a form factor? Come on, you must know this. I'm not gonna put you on the spot, so please volunteer.
How far away the particle is from a point particle.
Okay, and okay, part of it. There can be a lot of things that are away from a point particle. So form factor. So form factor, I wrote it, right? Maybe you didn't read it. Fourier transform of a charge distribution. So now you have an object, you have some electric charge distribution. And it's the Fourier transform of this distribution. It's like, a few steps. So now I wanted to give you an idea about what form factor. Hopefully this will stick into your mind for the rest of your life that you know what form factor is. So let me ask you a question. Have you played any music instrument, guitar, piano, things like that? Anyway, for the same musical note, why does the piano sound very different than violin?
Overtone series.
Right?
There's a different overtone series for different instruments.
Okay, very good. Do you guys understand what he said? Okay, maybe explain it to everybody.
So like for different instruments and different media, you have the fundamental frequency, but then you have also overtones at lower amplitudes, and different instruments have different overtone series.
Okay. Good. So let me give you this example, trying to elaborate. I'm not a musical guy. I'm a physicist. So this is something I found it tremendously interesting. Okay. So this is the study of the 4 different instruments playing the same note. And then the idea is that the pressure as a function of time, right? The sound wave travels. If you do a Fourier transform of this pressure distribution, it's actually the Fourier transformation is the frequency spectrum. So the frequency spectrum, you said, okay, the same note is the same frequency. It's kind of the same, right? The frequency is hertz. You have, 220 and some other peak. The peak position is the same. Different instrument sounds very different. It's because the distribution is very different. Okay? That is fundamentally why my voice is different than yours, different than everybody else, right? It's this Fourier transform of this pressure as a function of time, the pressure distribution, which is the Fourier transform of these. So this is exactly what happens for a proton charge radius or charge distribution. The proton charge distribution is this pressure as a function of time of the sound wave travels. And the Fourier transform of this charge distribution is this frequency spectrum. So we're actually looking at the same thing. We're trying to look at the different disconjugate variable, and then we can actually, so imagine that proton can be uniformly distributed, or the proton can be, very strangely distributed. It can actually translate it into a different frequency. It translates into a different sound, basically. So the idea of us is that we're trying to hit it, and we are trying to see what frequency that comes out. So that is what this charge distribution or Fourier transform of the charge distribution called form factor. So here is another way to intuitively understand is that fundamentally when you do elastic scattering, we call it diffraction. So you can think about it as using this particle, we have to remember this particle wave duality, that when you do an elastic scattering, we have the charge distribution and the form factor is this Q square, which is this frequency, right? Just the example I showed earlier. So that's the first column. This is going from, it's my stick. This is from proton. It's a very small object. And you do the Fourier transform. And that's exactly like doing a single slit experiment. You have a small slit and you have this diffractive pattern. So when you increase the size of your fundamental object, when you're doing this scattering, it basically you have a different size of your object and you do the Fourier transform, right? Remember this frequency? And this is exactly the frequency, right? So when you think about this, you already know the answer from the previous lecture. When you do a fundamental scattering, the photon has frequency, right? The photon is like higher frequency, lower frequency. This is exactly the same, right? So when you transform from a different size, you get a sort of different frequency spectrum. And this frequency spectrum, the physical meaning is that the slit is the size of your target. And you're going to have a diffractive pattern. So you can measure on the screen and infer what's the size or the form factor of the object. And this is exactly what the EIC will be doing, doing diffraction, using the fundamental scattering to understand the structure. Okay. By the way, AI wrote this. Okay. All right. So finally, moving to the 60s. So from Rutherford scattering, I will quiz you guys. Okay. Just remember this: Rutherford scattering, Moss scattering, and Hofstadter, and finally, eventually, to deep inelastic scattering SLAC. Okay. So this is a SLAC, you know, spectrometer. You have an arm, and you can change, and you do an electron because the energy can be increased. So this is the picture. I'm sure you guys have seen it 100 times. So now, this is the fun part. This is the elastic scattering. Remember, this is the expectation. Actually, this was the measurements that I showed you earlier, right? The Hofstadter has a very suppressed, much more suppressed than this. This is the Mach current. It's much lower for the elastic scattering. But what's strange is that they do this even higher energy. They crank up the energies. And finally, they see that it's not like this. It becomes almost like a flat distribution. And remember, the flat distribution means that you're hitting a point-like particle. And this is where that you discover actually there are fundamental point-like particle inside a proton. And that is the discovery of quarks, right? So the same logical steps has never changed. Only the technology changed. You increase the energy using electron to keep hitting, until it breaks. Until it breaks and not break again, which is this called inelastic scattering. We only know there was some objects inside of this, right? So that is the inelastic part is the quarks. So now, after that, in the 60s, with all of this, they actually get, you know, they call it this static quark model. This is something that people actually have come up with to put all these quarks into the model and how to form hadrons. You can have baryons, you can have mesons. So this is the famous eightfold way. Everybody have learned this in the quarks and leptons or your high energy quantum physics course. And you know, this is very successful in a way that you can just, you know, have strangeness, you have charge, and you put them on this kind of lattice, and then you can make particle. And they discover particles, you know, from that time, one day after another, you know, new particles show up every day. Think about publishing PRLs. If we do it, you know, the way we're doing now, it would be like one PRL a day, you know? You're discovering particles like crazy. I mean, LHCb still does that. But so Fermi actually famously said, if I could remember the names of all these particles, I would have been a botanist, right? It's just too many. So fast forward that this series, this very successful model actually has a serious problem. And so now you have all taken this class. So what is the problem of the delta plus plus? Anybody?
Color.
Color. Why? I mean, it's too brief.
Singlets. all the color charge cannot be unbounded. So you have to have like either pairs, like red or anti-red, or you need to have.
No, but that is the answer, right? Why something, they discover something is wrong? Why do we need a color in the first place? Come on, standard.
SU3.
Right.
And so if you have three up quarks in the system, you have one up, one spin down, and then what's the other one doing?
Yeah. Good. So it's because of the wave function, right? You have to be antisymmetric. So you actually need, so this is not the part I'm going to cover, but remember the series of events, right? After the quark model is very successful and they discovering all this particle, we call it particle zoo or whatever, and then you found there's a particle delta plus plus 3U quark. You cannot write down the wave function to satisfy the fundamental law. You need another degree of freedom to have this. And that is why the color was introduced. So finally, the QCD, the quantum chromodynamics, and that's what we do as a QCD. So we have three colors. This is our standard stuff that I'm sure that you have all seen because gluons, it's self-interacting. And that makes life so much harder, but makes life much real because all the visible matter, we call it the Higgs particle, the God particle. And then the gluons are the super God, right? Because everything is made of the gluons, we are all visible matter. So this is the gluons, and I'm sure that there will be a lot of lectures in the 2 weeks to talk about the fundamental QCD and also the relation to EIC. So at that time, at that time, gluons was needed because of the theory, because you have to explain things. So at that time, theory proposed there will have to be colors and to have to be gluons, and gluons will be the strong force carriers. But that was never discovered. How can you tell that gluon exists? And that is actually the 1979 the discovery of gluons. So this was discovered in Hamburg and this Peterrain. There were 4 experiments before Hera. They were doing E plus E minus, right? The E plus E minus energy is about 13 to 30 GeV. So usually, if you think about fundamental scattering, you have E plus E minus. You go quark, anti-quark. So now people in the 80s, people already understood very well the quarks, right? The quarks was, in the 60s. So if you have to have a gluon, that is where this so-called 3 jets events show up. So this is the discovery where in the detector, this is actually in LF. This is not in one of these original experiments. This one is in the original experiments, but the same thing. So when you have a E plus E minus scattering, you have a quark anti-quark pair, you have a gluon radiated out of the quark because gluon can be coupled with quarks, right? Because they share colors. So then you can actually have this, I call it the Mercedes plot. I don't know what you guys is gonna call it. In the hot pot, in China's hot pot, you also have a Mercedes, have spicy, non-spicy. So I call this a Mercedes plot. So this is, remember, the Mercedes plot is where we discovered the gluon. You have a back-to-back jet, but because you radiate a gluon, it basically balances it, and that is the discovery of gluon. Okay, and a lot of people said they should have won a Nobel Prize, which I think is definitely deserved, but they never got it. So finally, QCD is an emergent phenomenon, and I think Fred actually talked about this in the previous lecture, so that's why I'm not going to talk about it very much. The interesting thing is that for gluon, it serves as this force carrier, but it behaves very different than QED, right? Electromagnetic, because of these running coupling constants. And then when we have these large couplings, we call it this so-called the perturbative regime, the non-perturbative regime. You will start using this jargon more and more often later in this week. So one thing that is important, it's very interesting, is that this is a potential, and we all know from physics that from a potential, it goes to 1 over r to the kr. This is kind of the strong force, right? So let me now ask you, what is the force? What's the magnitude of the force at 1 Fermi, a strong force? Anybody ever thought about this? Take a guess. Yeah.
Isn't it about 0 at one Fermi, or is that less than one Fermi?
Definitely not 0.
I said about, but yeah, okay.
Anybody else? Take a guess. Come on. You're not gonna lose. We're not betting. Why don't you take a guess?
Well, I'm in the position there. I don't know.
Oh,
Okay. So you can try this at home. Take the derivative, try to figure out what's the force. So let me tell you the answer. More than 10 tons. Okay. You put in the right units, everything, actually at about 1 Fermi. And actually when you do the derivatives, this becomes a constant. And then let's say at the 1 Fermi, this is about 10 or 13 tons. You go hand on a few elephant on. Okay. That's how strong the strong force is. You need to have a feeling about this magnitude, right? The strong force at 1 Fermi, about 10 tons, which is amazing. So finally, this is my second to the last slides. My time is almost up. So this is the problem. We call it the confinement in QCD, because after we have from the Rutherford scattering, Moss scattering, and then we have the Hofstadter, the DIS, you think you know everything. But there are fundamental problems that we still haven't resolved. And we call it the QCD confinement. The question, sometimes in the EIC, we keep bringing up the confinement problem because the quarks and gluons cannot be separated, right? They always combine and confine, even though QCD as a theory is very successful. So what does that really mean? So this is the part I put up. So we're referring to the EIC Bible, the white paper, okay? So what we are trying to do at the Electron-Ion Collider is trying to further understand the inner structure of proton. Specifically, is this why the QCD confinement behave the way it is. So to rephrase it, this is the central question for the EIC. So if somebody asks you, what is the EIC is about? Throw up this sentence, so throw up this question to them, and that will be mostly correct, okay? People can argue with me, but what happened is that we do not understand how we know confinement exists because the existence of ourselves. What we don't understand is how confinement, why these quarks cannot be free. And when they combine, how do they show up as an emergent phenomena or emergent property as the fundamental building block, like protons and neutrons and nuclei. So you can rephrase it as how does the confinement manifest itself in the structure of hadrons and nuclei? So that's proton and nuclei in terms of their momentum distribution, mass distribution, spin distribution, and their correlation. So that is the problem that we haven't understood yet. And that is why we're building the Electron-Ion Collider to figure it out. It's not like what's inside. This is too simplified question. We already know what's inside. There are quarks, there are gluons. There are 6 types of quarks, right? There are gluons. We know the property very, very well by now. But we're still building this couple decades of efforts, putting billions of dollars to build this machine. The central question is trying to understand the inner working of the QCD confinement. And this is very hard to compute. And you will hear this from the theorists at the lecture, that this is very hard to compute. You need experiments to extract a lot of these parameters. So I will call it this, how does confinement manifest itself? Okay, so that's it for today. Thank you.
Thank you. That's a lot of questions. Now it's your time to retaliate. Any questions?
All right.